Okay, so we should have had an ellipse that had a x directrix of 3, so it comes out here to 3, 0, and then a y directrix of 2, so it goes up to 0, 2. So in terms of the direction of the curve, we have to go back to the original equations, and let's just use t equals 0. When t equals 0, what point do we get? You get 0, negative 2, is that right? And so when t equals 0, we are at the bottom of the ellipse. And one way you could find the direction is to say like t equals pi over 2 or t equals pi over 4, and then find out what that next point is, and that would indicate the direction. Okay, as long as that number is close enough to 0. So in this situation, pi over 2, pi over 4 would be fine. Okay, I'm going to talk to you about another way that we could find the direction of the curve, and so let's talk about this point down here. What can you say about dy dt and dx dt at this point down here? So is there anything you can definitively say about either one of those two at that lowest point on the ellipse? Dy dt or dx dt? Someone said both positive. So we think about changing t, so as t changes, we're going to get a different point, either to the left or the right. But right there for that value of t here, t equals 0, what kind of change in y do you get for a very small change in t? What kind of change in y do you get for a very small change in t? Very small change in t. What's your change in y? So I'm going to zoom in at that lowest point. Okay, so I'm zoomed way in. This is still the ellipse. This is still the ellipse, and I'm zoomed way in at that lowest point. What kind of change in y do you get for a change in t? 0, right? For a very small change in t, you essentially get no change in y. So what's dy dt at the bottom? Dy dt at the bottom of the ellipse is 0 because, why? Because for a change in t, for a very, very small change in t, there's essentially no change in y. So dy dt is equal to 0. And that can help us by setting dy dt equal to 0. In general, what points will you get on a curve? Points such that for a change in t, y doesn't change. So what could we say about those all points on the curve such that dy dt equals 0? Can we categorize those somehow? It's the same concept in Calc 1 when we took the first derivative and set it equal to 0. What did that give us? Remember? Places where the y didn't change for a change in x. Well, now we're still talking about y changing. So y has no change, essentially no change for a change in t. What very important points on a curve does it give us? Yeah, so like local max and local min. This is a local min. Just like in Calc 1, when you took dy dx equal to 0, you were saying, I want to know where, if I changed x a little bit, y wouldn't change. Well, that's going to be at the high point, or at the low point, or at points like this. If you remember in my class, we called them rest stops. So like that. That's also a place where, right there at the inflection point there is a place where dy dx would be 0. So also dy dt would be 0. For a change in t, you get no change in y. So this can be helpful for finding, just like in Calc 1, local maxes and mins. Okay, but so that was kind of a side conversation. We were really talking about the direction of the curve. So we know that dy dt will be 0, so that's not going to help us find the direction of the curve. Can dx dt help us find the direction of the curve? And how can it? Daniel, you nodded your head. How can it? Okay? What if the direction of the curve was counterclockwise? What would we expect about dx dt? If the direction of the curve was counterclockwise, yeah, so exactly, dx dt would be positive, right? If it's going counterclockwise, we'd expect dx dt to be positive. If it's going counterclockwise, then we'd expect dx dt to be negative, because for a change in t, you get a negative change in x. So let's do it. So rather than find another point, we can find dx dt here for this lowest point, which is, what's dx dt? And they all said in chorus, 3 cosine t, that's an easy one. Okay, and so then we want that at 0, evaluated at 0. It's going to be positive or negative? Positive 3. Therefore, the direction of the curve is clockwise or counterclockwise? dx dt is positive, meaning at the bottom that point, the change in x is positive to the right. So it must be going counterclockwise because the rate of change is positive. dx dt is positive. So if your initial point was on the sides, then would you check for direction? Would you check dx dt or dy dt? Like if you're out at 3, 0 or negative 3, 0 and you wanted to check direction from one of those points, you would check dx dt or dy dt. Because dx dt would be 0. Out at the left and rightmost points, your dx dt is going to be 0. There's no horizontal change for a change in t. But we can use dy dt to check the direction of the curve at a right or left endpoint. Okay, so there's a sketch, and the direction was counterclockwise. Counterclockwise. Any questions on the quiz, or this new way of looking at it? Okay, let's look at one more Weber problem. This one. Okay, so this is the equation of a circle. The equation of a circle is, and you may have had to brush up on this to do your homework, and so then the center is AB, and the radius is R. Okay, so this circle has what center? 9, 5, and radius of 4. So it's not going to quite make it to the x-axis. Okay? So we got this circle at 9, 5, radius 4. And so we want to write that circle with parametric equations. So again, we know that these circles, it all goes back to sine squared plus cosine squared equals 1. So we want to get this thing, we want to get our equation of the circle to look just like that. Sine squared plus cosine squared equals 1. And then we can pull out sine and pull out cosine from our equation. So what do we need to do to get this to look like that? Something squared plus something squared equals 1. First we have to divide by 16. So now we got the equals 1 down. So now we need to make, this is what we did Wednesday, we need to make that thing look just like all one thing squared and all one thing squared. And then we got it. Then we can just assign sine and cosine, but we had to stick with what they did. They did one of them for us. So what one thing squared is this? X minus 9 over 4, and then y minus 5 over 16. So now we can see that we could make substitutions or set these fractions equal to sine and cosine. It looks like they chose the first one to be cosine, right? The 9 and the 4 here. Sorry, 4, yep. Okay, so they chose this one to be cosine. You could also choose this one to be cosine too, but they chose x minus 9 over 4 to be cosine, and that's how they got 4 cosine t plus 9. That means we have two choices for this. What two possible choices do we have for y minus 5 over 4 that make it work? Yep, you could do sine or negative sine, and one of those is going to generate clockwise and the other will generate counterclockwise. So you get y equals 4 sine t plus 5. So look, here's the center of our circle. 9, positive 9, and positive 5. So when we change the direction of the, if we needed to change the direction of the circle, we don't want to mess with the center of the circle, right? Positive 9 and positive 5. That has to stay, right? We want to keep the same circle with center 9, 5. So those are locked. So to change the direction, it's only a matter of changing cosine and sine, making the cosine or sine opposite. So we need what? Clockwise. Clockwise is going to end up being, so because here we have x is cosine and y is sine, that's kind of our basic definition of cosine and sine. That sweeps a, what, if x is cosine and y is sine, we get that counterclockwise circle starting at the 3 o'clock position. So if they want clockwise, then that we can need the negative sign. But we can confirm that with a derivative, right? So let's confirm that with a derivative. So we think this is going to be, and we don't want to change the negative 5 because we need the center of that circle to be positive 9, positive 5. We're just changing the direction. So we're going to do this, make that negative 4 sine t. And so then if we, to confirm that, so to confirm that from this point, am I going to look at dx dt or dy dt? To confirm that we're going clockwise. Dx dt or dy dt? Dy dt. And dy dt is negative 4 cosine theta, or cosine t. At 0 gives us negative 4. Do I have it right? Does that give us clockwise direction? Clockwise should be that dy dt is positive or negative? Negative, heading down. For a change in t, dy is negative, heading down. So we got it. So that's right. Questions on this example? Okay, ready for new stuff. Last chance. Okay, so here is x equals t cubed minus 3t squared plus 1. Y equals the opposite of, or negative 2t to the 4th, plus 3t squared minus t plus 4. So you just apply a negative to all those, and we get this curve right here. So I'm going to investigate t equals 1. So first I want to show you positives. This is for increasing t, starting from negative 2 and ending at 2. So t from negative 2 to 2, I'm showing you how the curve is traced out for all the points that you get when t starts at negative 2, ends at 2. Okay? So that's showing you the direction of the curve. And then I want to focus in here at 1. T equals 1. So for t equals 1, you get this point right here. So I want you to find the coordinates. Got a list of things for you to do. Find the coordinates for t equals 1. Two, I want you to predict dx dt and dy dt, positive, negative, or 0. Don't find them, just predict. Is dx dt positive, negative, or 0? Is dy dt positive, negative, or 0? Okay, then how about dy dx? And I want you to estimate a value for dy dx. So you're reaching back to your knowledge from Calc 1. What is dy dx? And then predict second derivative with respect to x. Positive, negative, or 0. So take a couple minutes. So the arithmetic computation ends with question 1. You're going to do a little bit of arithmetic for question 1, but then it ends, and then it's just discussion based on what you're seeing. You're going to predict dx dt and dy dt just positive, negative, or 0. I want you to estimate a value for dy dx, and then predict the second derivative with respect to x, positive, negative, or 0. Go, take a minute or two and talk amongst yourselves. Everyone get a partner and talk. Everyone's talking to somebody. Find someone to talk to. Everyone has a partner, maybe a group of 3.
Okay, so
Okay, you should have confirmed that at t equals 1, it's negative 1, 4. Is that right? X is negative 1, y is 4 when t is positive 1. Is that right? Okay. How about dx dt? So dx dt, positive, negative, or 0? So what are we saying? For a change in t at t equals 1, is dx dt positive, negative, or 0? What is dx at t equals 1? Everyone votes. Everyone votes. How many people say positive? Everyone takes a vote. How many people say negative? How many people say 0? Okay, the negatives have it. Why? Because at this moment, for change in t, the next point would be a little bit to the left. So that's negative. What about dy dt? Positive, negative, or 0? Negative again, because for a change in t, the new point that you would find for a change in t would be lower, right? So you'd have a negative change in y, or the next point would be down below this point. Okay, estimate a value for dy dx. Estimate a value for dy dx. So what did you come up with? What does it mean? It means for a change in x. How much does y change for a change in x? Yeah. What's that? Negative 2. What do you think? Negative 2.
So we thought negative 2 at first 2, but then we realized that if we're going to the right, then it goes up, so positive 2.
So positive 2. So we got negative 2 and so well, let's just say, is it dy dx positive or negative? Yeah, so dy dx is going to be the same dy dx that you did in Calc 1. So if we thought about zooming in, that's what I want to do. I want to draw attention. Close enough? I'm going to zoom in. Okay, dy dx, positive or negative? It's still rate of change, y with respect to x. So if x changes a little bit, does y increase or decrease? If x increases a little bit. No, if x increases a little bit, not t. Yes, the direction of the curve is this way, but if x increases a little bit, a small positive change in x, what kind of change in y do you get? Positive or negative? Positive. And it's a positive slope. So it's still the same dy dx you've always had, even though for increasing t, the curve goes that way. The direction of the curve is down and to the left. You still have the same dy dx you always had. Okay? So let's actually find the value of dy dx. Okay, so quickly, why is the point not on the curve? Why is the point not on the curve? Okay, because to graph this, I want you to think about it. Think about how my graphing software would be graphing this curve. It has to do with that. So if you're curious, you can think about it, and then you can ask me. Okay, but there's a very good reason why the point is not on the curve, because of how the software generates the curves. Okay, and I'll let you think about it. If you can't live without the answer, you can talk to me. Okay, let's actually find dy dx. And so we can find dy dx. So first of all, can we find dy dx by writing y as a function of x? So let's look at this. X is a cubic, y is a quartic polynomial. And we want to try to solve for t and plug that into y. What do we think? No, we don't like that. That's no. Right? No. Yeah, so that it's like, and what y is, so this is certainly not a function of x, right? It would take multiple equations to do this, because y is not a function of x. There's lots of values of x for which you get more than one value of y. So because of the nature of this parametric equation, writing it as y is a function of x and then finding your dy dx isn't going to work. What we can do easily is get dx dt and dy dt. So what is dx dt? We long for the days of doing problems like these, right? Dx dt, dy dt. So I'm just going to distribute the negative. So negative 8t cubed plus 6t minus 1. Okay, and where are we at? We're at x equals 1. or sorry, t equals 1. So dx dt. Now, before we do that, I'm going to show you that we can simply get dy dx by taking dy dt divided by dx dt. The math works out, right? The dt's go away. So we can think of dy dt as change t a little bit. What change in y do you get for that change in t? And then similarly, change t that same little bit, and what change in x do you get? So by the math, dy dt over dx dt is going to be dy dx. But notice that dy dx now is a function of t, not a function of x. So we have dy dx, but the variable that we need to get those is because that's an expression of t. So dy dx equals negative 8t cubed dy dt over dx dt. So the meaning is the same meaning you had from Calc 1, but it's not a function of x like you had in Calc 1. It's a function of t. But that's fine because we wanted to get dy dx at t equals 1. So what will it be? So at 1, negative 8. So is that negative 3 on the top? Check my math. And negative 3 on the bottom. Positive or negative? Positive 1. This close-up version kind of helps you see so it's 1. So for a small change in x, the change in y is the same as the change in x. dy over dx is 1. What if we wanted to write the equation of the tangent line to that point? So the equation of the tangent line at the point negative 1, 4. We've got everything you need. Piece of cake, right? You got the point, negative 1, 4, and you've got the rate of change, 1. So we can use our point slope form. Y equals m x minus the x1 so 1 times x minus, what is x? Negative 4 or negative 1 plus 4. So it's going to be x plus 1 plus 4 or x plus 5. Did I do all the math right? All right, let's graph x plus 5. What should we see? There's y equals x plus 5. Equation of the tangent line. Has the same rate of change. Goes through that point, negative 1, 4. Questions? Okay, what about the second derivative? So did you predict the second derivative? Remember from Calc 1. At this point, is the second derivative positive, negative, or 0? Positive, negative, or 0? Do you remember what second derivative has to do with the curve? So it tells you how the first derivative is changing, right? It's telling you if the first derivative is increasing, decreasing, or staying constant. So is the first derivative, so now again, this is for a change for x increasing, right? So for x increasing, is the rate of change increasing or decreasing? That's what we're asking. So for increasing x, not for increasing t, for increasing x, is the rate of change increasing or decreasing? We're increasing x. So we're increasing x, thinking about rate of change visually this way. So is the rate of change dy dx increasing or decreasing for increasing x? You should be thinking decreasing. High positive, decreasing positive rates of change through here. So does that mean the second derivative is positive, negative, or 0? How many? Everyone votes. How many vote for positive? How many vote for negative? Okay. And then we said when the rate of change is decreasing, you get a concave down shape. Concave down was the second derivative's negative. Remember that? So how do we find the second derivative? We've got the first derivative in terms of t. See this? So we can't take the second derivative by taking the derivative of that. Why? Because that's with respect to t, and we need a second derivative with respect to x. So what we're going to do is we're going to do the same thing we did to get the first derivative. Okay, we're going to do the same thing we did to get the first derivative. We're going to take this is what we want. This is what we want. But we can't take it with respect to x because our function is with respect to t. Do you see that? We can't just differentiate the first derivative with respect to x with respect to t. So we're going to just apply the same exact strategy that we did to take the first derivative. We're going to take the derivative of the first derivative with respect to t. And then divide that by the derivative of x with respect to t. So this is exactly the same thing. And the resulting is the derivative of the first derivative with respect to x in the end. So we're applying the exact same strategy we did to get dy dx. Now to the second derivative. Take the second derivative with respect to t divided by dx with respect to t. So what does it mean to take the derivative of this with respect to t? What do we need to do? How do we take the derivative of that with respect to t? Do the derivative of this divided by the derivative of this? Must be Friday. How do we take the derivative of a quotient? It's going to require the quotient rule. Over dx dt. We already know what dx dt is. What's dx dt? This one. 3t squared minus 6t. So it's the quotient rule on what? On dy dx. What was the quotient rule? Low d high minus high d low over low squared, right? Denominator times the derivative of the numerator minus numerator times the derivative of the denominator over denominator squared. So it's just a bunch of algebra. And then what will we do? We're going to plug. Then once we find that quotient rule, that'll be here, and then 3t squared minus 6t there. Then we're going to plug the 1 in, and we expect to get a negative result. We're not going to take the time to do it, but you should be able to see the roadmap very easily. It's just algebra from here. Apply the quotient rule to dy dx. Divide that by dx dt. That will be your second derivative, dy dx. But again, it'll be a function of t. We'll plug t equals 1 in. We're going to get a negative number because we're concave down there. Questions on the second derivative? Okay, we're going to change gears a little bit here. Last chance for questions. Let me just write here. Plug in 1 to the whole thing, and then we expect negative. Why? Because we're concave down. Rate of change is decreasing for increasing x. Last chance. Questions? So now I'm interested in, I want to know the rightmost point of this curve. I want to know the point on the curve that's the furthest to the right. So if this, so it would look like a anteater or something. Aardvark. Does it look kind of like an anteater? So if this anteater was running at a vertical wall, over here, it was running towards this wall. At what point would it strike the wall? Okay. Well, that sounds like a guess to me. How we want to do it mathematically. So if you didn't, if you couldn't see the, I don't know exactly at what point would the anteater strike a vertical wall if he was running toward it. How am I going to do this? How am I going to use math to figure this out? Yes, sir. He wants dx dt to be equal to 0. Does that make sense? Dx, meaning for a change in t, we're looking for a point where there's no change in x. Would that be at the rightmost point of the curve? Yeah, we talked about that earlier in class with the ellipse, right? Yeah, that's right. At the rightmost point, the direction of the curve is vertical, right? The direction of the curve is exactly vertical. And so we know that that's where dx dt is equal to 0. So let's do it. Ready? So we're going to take dx dt, which we already found, 3t squared minus 6t, and we set it to equal to 0. So we're saying we want places where if you change t a little bit, x would not change. That's going to be places where it's heading vertically, right? So we're going to factor this. And we get two values. T equals 0 and 2. T equals 0 and 2. So let's find those coordinates. Well, before we do that, let's zoom out. Is there one or two places where this thing is heading vertically? Is there one or two places where it's heading vertically? It sure looks like just this one point over here. So which one is that? Yeah, that looks like that's going to be our t equals 0. So let's at t equals 0. What point do we get? It's the point you guessed by looking at the curve. When t equals 0, we get, is it 1, 4? Okay, so there it is. At 1, 4, we just confirmed that it's heading vertically at t equals 0 at 1, 4. But what about this other one, t equals 2? So what we don't see from this view is, you need to zoom out. This curve actually, it looks like it's heading kind of to the left, but then it actually kind of curves back. And there's another place where it's heading vertically here. So like it's a local leftmost point, right? So at that point right there at t equals 2, it's a local leftmost point. And so what is that? 8 minus 12 plus 1. Is that negative 3? No. Yeah, negative 3. And what do we get when we plug in 2 into that? I'm going to cheat. Negative 18. So at negative 3 comma negative 18, when t equals 2, we have another place where dx dt equals 0, meaning a vertical tangent, or it's out of the local leftmost. And local because we know there's another point over here that's further left, but in the local vicinity, it's the furthest left. Okay, so how would we find, I want to find local max and local min of this curve. How would we do it, and how many do you expect? Tuck. How do I find local max and local min on this thing? How do you do it? How many would you expect? Okay, so what's the general strategy going to be for pinpointing local max and local min? What am I going to do mathematically to find these places? Because these are not at nice places we can just find by eyeballing it off the curve. So I need the mathematics to get the exact t-values and coordinates for local max and local min. What am I going to do? Who's paying attention today? Right, we want places where for a change in t, y doesn't change. Horizontal tangent. Horizontal tangent. For a change in t, y doesn't change. dy dt equals 0. How many do you expect? How many people say 1? How many people say 2? How many people say 3? How many people say 4? There are 3. There's going to be one here. There's going to be one right there. And there's going to be one right there. So what do? We're going to take that equal to 0, find the roots, the derivative of that, so dy dt. It's going to have 3 roots, 3 values that make it 0, and those values of t will be the t values that generate those 3 ordered pairs. You have 2 local maxes and 1 local min.